Okay, welcome back again. Chemistry 3202 course overview review. We're looking at a new unit this time, Unit 2, Section 1, Lesson 1. We're going to look at some definitions of acids and bases. Up to this point, I think I got definitions spelled wrong there. Up to this point, you should have been taking advantage of our online tutoring and our online material. Lots of stuff there to help you out. Lots of public exam review questions there. So make sure you go check them out. So here we go, acids and bases. This material is chapter 14 of your textbook, page 544, and there's a few questions on page 542 and 552 that you can have a look at. These are the outcomes for this lesson. Okay, operational definitions of acids and bases. All right. An operational definition of anything, I guess, is simply a definition of observable properties. What do you see? What do you notice when you look at something? How would you define it based on its behaviors, what it does, and what it looks like? So, for example, operationally, metals are defined as something that's shiny, malleable, you can pound it, ductile, you can bend it into wires. They can conduct electricity. They're solids at room temperature. And it's just simply looking at a metal and seeing what it does. In no way, shape, or form is this definition trying to explain why metals do all that stuff. So that's what an operational definition is. It's simply looking at what acids and bases do. And the earliest definitions of acids and bases were very operational. People really didn't understand why they did what they did. They just simply knew what they did, and that was good enough for what they needed. So, for instance, they knew that if something tasted sour, like a lemon or a lime or something like that, they knew it was responsible because there must have been some acid in that orange or lemon or lime. They also knew that acids could dissolve metals. They also knew that bases were things like soap, that were very bitter in flavor, and you can make it from wood ash and seaweed and things like that. Very good cleaners. All right. Now, in no way, shape, or form do they explain why these acids and bases do what they do. So they are simply based on what they look like, what they did, and some of their uses. What was some applications for these acids and bases? So what we want to do is there we go. So an operational definition makes no attempt to explain why the substance does what it does. All we know is it does it, right? And generally, an operational definition doesn't really give us any clue as to how we could identify new substances that would have the same behaviors, all right? So it doesn't give us any idea of the composition, what it's made up of. It doesn't really explain anything about what it does or why it is what it is. All right, so operational, no attempt whatsoever. It's simply an observation of what it does. Now, if we look at some operational definitions of acids and bases, we've already listed a few, and you guys should be familiar with many of these. You know, we said an acid is a species that forms an aqueous solution that, number one, we can do a simple test on it. It turns blue litmus red, ABR, acids turn blue litmus red. So if you have a fish tank or something like that and you want to make sure that the water in the fish tank is not too acidic, you might go to the local pet store and get some litmus paper. When you tip in the blue litmus paper, it turns red or a pink color. That would be an indication that your goldfish water is pretty acidic. So ABR, acids turn blue litmus red. Now, did we explain why it does that? No. Operational definitions don't do that. All we're saying is dip that piece of paper in with litmus on it, the litmus turns from blue to red. ABR, acids turn blue litmus red. These guys neutralize or partially neutralize bases, so it's an arch enemy of a base. Generally speaking, these guys will be classified as anything with a pH less than 7. That's a new term there. Did we explain what a pH is? Absolutely not. Does everyone understand it? For the most part, everyone knows that 7 is neutral and everything below that is very acidic. Okay, we looked at this idea of that acids generally taste sour. You know, we make sweet and sour sauce out of acetic acid and a bit of sugar, and it's the vinegar that gives us the sour taste. Tart and tiny candies made of tartaric acid. Okay, cream of tartar we like to put on our fish, made with tartaric acid as well. Okay, these guys react with metals to produce hydrogen gas, and finally, these guys conduct electricity and are known as electrolytes. So they're able to conduct electricity. And some common examples, I guess, of some household acids that we would have around us, right? We would have acetic acid, which would be vinegar. Muriatic acid we would use if we were into bricklaying. We would be able to clean the bricks and concrete off with it. It would dissolve the concrete. That would be the hydrochloric acid or muriatic acid. And there's a whole bunch of these that we could list. Okay, bases. These guys are the arch enemies, I guess, of acids. Whatever these guys do, then the acids and bases do the opposite. All right, so these guys are going to be species that form basic solutions that would turn red litmus blue. BRB. Be right back. All right, that's how we remember it. Be right back. Bases turn red litmus blue. Always a multiple choice on the public exam on this operational definition. These guys would neutralize acids. Obviously, if acids neutralize bases, then bases do the opposite, so they would neutralize the acids. These guys have pHs above 7. These guys would taste bitter, like that dry, pasty taste from soap. If you've ever had your mouth washed out with soap, you know what we're talking about. If not, go and grab a piece of soap and start gnawing on it and see what it tastes like. That's bitter. These guys feel slippery like soap, shampoo, things like that, very slippery. And these guys also conduct electricity, and these guys are an electrolyte. And some examples of these guys, I guess, would be like liquid Drano, which would be sodium hydroxide. All right, soaps, detergents, things like that. These guys would be bases. Mr. Clean and things like that, right? Okay, here we go. So again, no attempt to explain why they do what they do. Here's a little schematic diagram showing you some of the everyday items around us. Like for instance, here would be neutral water. Pure water would be fairly neutral. Blood is around 7.5-ish. Milk is about 6.5. There's a banana. Banana's slightly acidic. Apples, depending on what variety of apple you have, like a crab apple would be very acidic. Tomatoes are down here. Vinegar, lemons, limes, and there's your hydrochloric acid, very corrosive. Okay, on the basic scale, anything above 7 would be basic, and we can see baking soda, soap, ammonia, like Windex and things like that. Drain cleaner, very, very corrosive. You don't want to get that on your hands. And there we go. So lots of household items there. So we want to be able to look at this. Now, anyone in science looks at this and says, yeah, okay, that's an observation, but why? Why does it turn blue litmus red? Why does it neutralize a base? How does that work? You know, what's the chemical formula? What's the breakdown? How is it behaving? Why does it do what it does? So we want to be able to try and explain why these things are acids and some other things are bases. And we want to come up with what's called a theoretical definition now, which is going to try to explain what these acids and bases do. And the first definition we're looking at that's theoretical was the Arrhenius definition. Now Arrhenius, the scientist who looked at this, he wanted to try and group these things together. And he said, all right, just about everything that was in the acid category, so everything that behaved as an operational acid, who does all the things acids do, what he noticed is that most of these things generally had a hydrogen in its chemical formula. And he said that these guys would break down, they would dissociate in water to produce a hydrogen ion and the associated anion that would come along with the hydrogen. So in this case we get hydrogen and chloride. And it would be the separation of the hydrogen chloride that Arrhenius says was responsible for making this behave as an acid, because it was this free hydrogen that was giving it its acid properties. When he looked at the bases, he said, okay, these guys are different again. And when he looked at something like sodium hydroxide, he said, hey, this is sort of doing the same kind of thing. It's dissociating in water, but in this case we're getting a hydroxide ion, which now the hydroxide ion, Arrhenius said, was responsible for all the base things that were going on there. So this is nice and convenient. That's a nice little theory. So now we can start looking at this and saying, very theoretical, because now we can explain what's causing the acidity or the alkalinity, the basicity. And also now we can start looking at new substances and say, let's look at their formula, and because it has a hydrogen, we can make a prediction that, yeah, that should be an acid, and because something has OH, it should be a base. So it's a theoretical definition, and this is the first one. Now, when we look at these theoretical definitions, this is how science progresses. Someone comes up with an idea and tries to explain things, and then someone else looks at it and says, yeah, hold on, that's okay for the ones that you've listed, but what about these examples that you can't explain? So here's the first piece of conflicting evidence that came up that was kind of against what Arrhenius was saying. Some other scientists looked at this and said, hey, look at bicarbonate. This could be from something like sodium bicarbonate, baking powder, baking soda, potassium bicarbonate, any bicarbonate there. We're getting the bicarbonate ion, and we're looking at this and we're saying, hey, that has a hydrogen in it. So at first glance, would you expect this to behave as an acid? And you say, yeah, because it should give up hydrogens. All right, the problem with this is that when we tested it from an operational perspective, we found out that even though we expected it to be an acid because of that hydrogen, it really behaved like a base. It was be right back, right? Bases turn red litmus blue, so the bicarbonate turned the red litmus blue. Okay, I got that backwards there. Turn the red litmus blue. It was slippery. It neutralized acids. If we have a battery acid spill in our garage or something like that, sulfuric acid is spilled all over the bench, you go get some baking soda and sprinkle on it and that'll neutralize it. So it's acting as a base. So this bicarbonate is acting like a base even though, according to Arrhenius, it should appear to act as an acid. So that's not correct. There's something going on there. There's another one that we can look at too. We look at ammonia, NH3. Look, it's got 3 hydrogens, so that's definitely going to be an acid, you think? All right, well, let's go test it. Go get some Windex and do all the things that you would expect it to be. You'd expect it to be an acid. However, when you tested it, you found out that it was actually a base. It turned the red litmus blue. It was slippery. It neutralizes acids. It does everything that a base does. So we're saying, well, what's up with this? What's Arrhenius talking about here? He can't be possibly right. And another group of people started to weigh in on this as well. The idea, physicists started to weigh in on what Arrhenius was saying, because you're saying, hey, if you're going to tell us that this particular hydrochloric acid is going to dissociate to give H plus and Cl minus, let's just back it up a little bit. Let's just back this up a little bit and saying, okay, the hydrogen acting as a proton is essentially H plus, so it only has 1 electron. Hydrogen only has 1 electron. It just gave it up. So now it's got 1 free proton. So you're saying, yeah, okay, that's okay for chlorine, because chlorine would gain that 1 electron, and now it has an octet rule here, and this is fair enough for chlorine because now chloride has been stabilized because it gained 1 electron. But poor old hydrogen is here, and it's lost its only electron. So the physicists are looking at this and saying, well, that's not good. In order to make this hydrogen, it gives up its only electron. And how can this possibly be stable? And here Arrhenius is saying, yeah, that's going to be floating around in water. No, that's not going to happen. It's not possible because it's not going to be stable floating around by itself. So as a free-floating proton, it's going to be immediately taken up and attracted to some other species. It's a very unstable species. So the physicists are looking at Arrhenius' theory and saying, you better come up with something different because this just doesn't cut it. It's no good. It doesn't work. All right, so Arrhenius took this into account, and he said, all right, I'll change my ideas. I'll change my ideas. What he came up with is he said, all right, instead of having the hydrogen floating around by itself, let's have an actual chemical reaction with water. So as the acid gives up its hydrogen, the acid actually reacts with the water to produce something called a hydronium. Okay, so this would be the hydronium. H3O plus would be the hydronium, and we would still get the chloride because chloride was okay. And he said the base would do a similar sort of thing, whereby the base would actually react with water to produce hydroxides, which is the same as what he was saying before, but now he's got the reaction with water brought in here. So he's saying I can explain bicarbonate. Bicarbonate reacts with the water, and in doing so, it produces H2CO3, and here we go. We get the OH minus. Okay, so in that case, it's okay. Okay. The other thing he said was, well, let's look at ammonia. And he said, same thing. Ammonia can react with water. It's going to produce the OH minus and an H4 plus. Perfect. All right, everything is okay. Everything has an octet rule. The charges are stabilized. Everything is perfect. So the modified Arrhenius theory is working out. What do the physicists say about this? Well, so far so good. So by changing his ideas, modifying his theory, he says, I can explain bicarbonate, I can explain ammonia. And he tries to offer an explanation to the physicists. And he says, all right, here we've got water, and this hydrogen here, which has no electrons, is going to be associated with the lone pair of this water molecule. And in a sense, the formation of this complex ion has a stabilizing effect on the hydrogen, because now that positive charge is equally distributed around this entire complex molecule. And this idea that the hydrogen ion now has been stabilized because of its attraction to that lone pair, physicists say, yeah, okay, perfect, Arrhenius, deadly, works for me. All right, so we solved three things here, and we're looking at this and we're saying, oh no, not some more conflicting evidence. What's going on here now? How could he possibly be wrong? And we're looking at this and we're saying, okay, you're telling us that bicarbonate is going to react with water so that it's going to get that hydrogen and we're going to get OH minus. So we're saying, well, why couldn't the bicarbonate react with water to form H3O plus like hydrochloric acid did? Why can't this be possible? So bicarbonate here is doing two things. In one situation, we're showing it acting as a base because it's producing OH minus. And in another situation, we're showing it acting as an H3O plus. So we got a little bit of a conundrum here. People are saying, well, how can it be both? How can something be an acid in one situation and a base in another? And Arrhenius was a little bit perturbed by this, I guess. All right, he really didn't know how to come back with this. And we're going to explain what they come back with in the next lesson. So what we want to do is quickly write some expressions here showing these guys acting as acids and bases. So in this case, hydrocyanic acid. This is HCN, and again, it's going to react with the water to produce H3O plus. There we go. It's acting as an acid, and we get some cyanide ions. Okay, perfect. The next one, nitrous acid, HNO2. Okay, we can show nitrous acid reacting with the water, again, to produce H3O plus and nitrous ion. Or nitrate ion. There we go. So that's an acid. Potassium hydroxide, not a problem. Now, rather than try and bring in the complicated business of water here, we're simply saying that the hydroxide is present here, and that's what Arrhenius said you required for a base, was the presence of hydroxide. So there we go. Dissociation of potassium hydroxide in water, aqueous solution, to produce potassium ions and hydroxides. Perfect. That's going to be a base, and it is. And last but not least, calcium hydroxide here. And calcium hydroxide, once again, can dissociate in water to produce calcium ions and 2 times as much OH minus. So this guy's going to be a wicked base because it can produce 2 times as much hydroxide. There we go. Okay, next lesson we're going to look at how Arrhenius, or how they got over this idea of something able to be an acid in one situation and a base in another. And at this stage, I'm going to stop. Make sure you take advantage of our tutors and the online content. And if you have any questions on this, don't hesitate to drop a question in the discussion posting, and I'll try and get back to you within the next lesson. All right, see ya.